Howdy. I just wanted to say something about Becca's question regarding the new investigation. So one thing I'll note is some of the videos on this were going up tonight, so that might be part of the challenge. So I was going to preload with this short little thing on some of the sequence limits data you might need to do this problem. So this is just a nice little exploration. This is an example of a recursively defined sequence, and there are lots of sequences sort of this general type. They're the ones that are all either called continued roots or continued fractions, and one of the options for a video problem is a continued fraction example. So in this one, though, you're told that we're looking at this expression, the square root of 1 plus, 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 so on and so forth, where each root is underneath the others. And so what I'm going to apply in order to solve this problem is the theorem about bounded monotonic sequences. So the bounded monotonic sequence theorem of course, I find the one place with glare. Let's see if I can fix it. Bounded monotonic sequences theorem. And what it states is that if you have a sequence, A sub n is either bounded above and increasing, meaning every term gets larger than the one before it, or bounded below and decreasing, in either of these cases, then the sequence A sub n converges, and in the increasing case, we know it converges to a constant that must be less than or equal to the upper bound you found, and in the other case, greater than or equal to the bound. So to say something is bounded above, I mean that A sub n is less than or equal to some upper bound m. I said m and then I wrote b. We'll call b. Upper bound b. So there's some constant b such that every single term of the sequence A sub n would be less than or equal to b. And then to say it's bounded below means that there is some little number, little b, that is smaller than or equal to every number A sub n. So you can think of this as an adjustment of the squeeze theorem when you only have a bound on one end. And it's not as specific as the squeeze theorem in that it can't necessarily tell you the limit of the sequence. It is only telling you that there is a limit to the sequence. And there are lots of cases, especially as we get into series, where this is an important thing. Just to know that a sequence converges at all is a start. So the idea is this even a number, this expression? Or is it something that as you add each layer of the little square root, does it grow, grow, grow? Even knowing whether or not, what kinds of things this exceeds can be hard. So to start out in the beginning of this, go ahead and the first part said, write the first few terms of the sequence. And this is how they suggested you think about this sequence. They said, consider the first term to be 0, and then have any other term be determined by taking the square root of 1 plus the term that came before. And we can see that that is a way of describing the sequence as we go along. In order to build this, let me show you why. So if we follow these rules to create the sequence, then we know what the first term is. A1 is 0. So A2 should be the square root of 1 plus 0, because that was A1, so just 1. A3 should be the square root of 1 plus A2. So it's the square root of 2. And then A4 is going to be the square root of 1 plus the square root of 2. Okay. A5 is equal to the root of 1 plus everything from before. Root 1 plus root 2. And so then A6 is going to introduce another root and another root and another root. So the idea here, we have this one. We're kind of comparing it to one where we're building it out from the bottom up, where we sort of know what the innermost part is. And the fun thing is we're going to discover these in a second. So the first thing you're asked, you see, that's the first thing, is just to look at some of the terms. From here, we're supposed to say, show that every single term must be less than 2. So you want a logic for why that would be the case. Well, we know that 2 is equal to the square root of 4. So I'm guessing one way you could go about this is maybe show that a sub n plus 1 squared has to be bigger than 4, or smaller than 4. That would probably work. But this, it's fine, in these investigations, if you want to just try to run it for a ton of terms, see the trend, it's actually bounded by much less than 2, but yeah. So that's the process there. And then as you go through this, you'll probably see a trend in the behavior. But if I can establish that there's an upper bound, the other thing I need to do is show that the terms are always increasing. So I would need a way to argue why something like this has to be bigger than the previous term. And so you'd have to think a little bit about that. What is it that's making it bigger? How is it going to be an increase from what I had before? And you need that if you're going to be able to establish that it's increasing and bounded above, by which we can use the bounded monotonic series or sequences there. So I'm purposely not giving more away than that. But I hope that helps a little bit in giving a feel for what's going on in this application investigation, and I encourage you to share ideas with me.